Good afternoon, everyone. I'm Andrei Faraon from Applied Physics. Welcome to the KNI Distinguished Seminar Series. The speaker today is Professor Jelena Vučković from Stanford University. Actually, she's my PhD advisor. So at Stanford, Professor Vučković is professor in electrical engineering and also by courtesy of Applied Physics. And also she leads the nanoscale and quantum Photonics lab. She's also involved in a lot of initiatives related to quantum photonics centers at Stanford, like QFarm and Stanford SLAC Quantum Science and Engineering Initiative, and a couple of others. So Jelena is also a PhD from Caltech. She got her PhD Professor Axel Scherer in 2002. And since 2003, she started her faculty position at Stanford. Besides being a professor at Stanford, she also has affiliations with Max Planck Institute for Quantum Optics, where she has a visiting position. This is in Germany, in Munich. Also with the Institute for Advanced Studies of the Technical University in Munich. And also she was affiliated with the Institute for Physics of the Humboldt University in Berlin, in Germany. She received many awards. Some of the recent ones are the A.F. Harvey Engineering Research Prize. She's a distinguished scholar of the Max Planck Institute for Quantum Optics. She has the Hans Fischer Senior Fellowship for the Institute of Advanced Studies in Munich, and also she received the Humboldt Prize in 2010. Today she will talk about some of the recent work that spans from the inverse design in nanophotonic devices to quantum photonics. Please.
Thank you. Thank you very much. Thank you very much, Andrei, for your kind introduction. It's a great pleasure to be here. As Andrei mentioned, I was a Caltech graduate student, so I used the brief break before the seminar to grab some Caltech swag from the bookstore for my kids. And it's great to be here and see my PhD advisor, my PhD thesis committee members. Professor Amnon Yariv was basically my co-advisor. Andrei is my PhD student, so it's just a great honor to be invited to tell you about what we're up to and what we're doing in my group at Stanford. Andrei said that I'll talk about our work from inverse design to quantum optics. About half of my group at Stanford works on really experimental quantum optics, and the other half of the group works on classical photonics applications and nonlinear optics. So I'll try to kind of give you an overview of everything that we're working on. And the link between those different pieces is this inverse design method that we've also been working on for more than a decade, which results in some very non-intuitive structures that I'll be describing. This is, for example, some WDM device wavelength splitter, and this is basically a stage of a particle accelerator that I'll also be describing later, both of these in silicon. So let me start with a kind of an overview of what's going on in photonics for those of you who are not really actively working on photonics. Photonics is, of course, very active area of research these days, and it's also of great interest to industry because of a lot of potential interesting applications. And these applications really range from optical interconnects in data centers to a lot of imaging applications, augmented reality glasses, you have LiDAR systems, optical information processing, and even quantum information processing, where eventually you have to connect systems by using optics. But for pretty much most of these applications, you can't really use free space optic solutions because they're very large. If you're building augmented reality glasses, they have to be really small so that people actually want to put them on their head. So you're constrained by the footprint for many of these applications, and you have to find solutions that are really compact and efficient and would work out well. So the question really is whether you can go through the same transition in photonics that we went through in 20th century with computer industry and with electronics, where from state-of-the-art computers that occupy the whole rooms in mid-century, right now we have way more powerful computers inside of our mobile devices. And we've been wondering about this for a long time. Of course, a lot of people work on integrated photonics, But it turns out that a lot of integrated photonics components are not very suitable for this high density integration that we're talking about and high efficiency integration that would be comparable to what we have in electronics. A lot of state-of-the-art photonic components are pretty large. They're way larger than electronic components. They occupy tens of microns of space on a chip at least. They're very sensitive to fabrication errors, temperature variations, and that's why you often have to incorporate a lot of tuning elements, as you see here, to kind of tune everything back on resonance, and those tuning elements often consume a lot of energy, lead to losses in the system, and complicate the circuits. Then they're designed by manual tuning of few parameters. A lot of designs that we use in photonics actually had been adopted from microwave engineering from many decades ago, where people could design things only by hand. So there is really no reason to believe that a lot of the designs that we use are optimal designs. And finally, as a result of all of this, even in commercial systems, a lot of components that we have are not very efficient. Even input couplers from fiber to chip have efficiencies on the order of about 40%. So you're really throwing away a lot of the power before you even use it for some sort of information processing. And in my group for more than a decade, we've been wondering whether we could solve things much better than this, so that we could enable this high density integration, high efficiency integration, which is how this work of inverse design happened. And this was the list of things, the wish list of things that we wanted to achieve: better device performance, smaller footprints, new functionalities, instead of being constrained to few limited functionalities from the very well-known library of devices that you learn in grad school or in optics classes. Can we eliminate this brute force design from the design process so that you can truly design optimal solutions that are efficient for particular applications? And can we even enable, develop tools where electronics designers could design optics, so that they really don't have to have a PhD in optics to design optical circuits? And we succeeded in this initially about 7 years ago, when we developed the first three-dimensional inverse design tool, which was successful in designing some of the initial devices. But we've come a long way in this process, and pretty much everything that you'll see today in my talk has been designed using this inverse design process, because for a lot of applications, we actually really didn't even have traditional photonic solutions. We just had to ask computer optimization tool to design things for particular functions. So a lot that you will see looks like this. These are actual blocks of silicon, wavelength splitters. I'll describe this a little bit later. So highly non-intuitive, but much more robust to a variety of errors. In temperature, fabrication, we incorporate all of that into the design. And if you're new to this area of inverse design in nanophotonics, which is really booming and is becoming pretty much mainstream in a lot of photonics work, we wrote a review article with Alejandro Rodriguez from Princeton that was published last year, which gives you an overview of all of the activities using inverse design in various areas of photonics, from metasurfaces all the way to silicon photonics. So without going into details of what we're doing, I'll just kind of describe in a few minutes what is going on here. We're basically using powerful optimization techniques, classical optimization techniques, kind of variations of gradient descent, in order to efficiently search through the full parameter space of fabricable devices. And this movie here will show you how design of mode converter looks like. And mode converter is just something that's supposed to convert first order mode to a second order mode, and this is a crosscut of the design process. So this is an initialization stage, and this is the second stage where we design something that we can reliably make. Efficiency of this is incorporated into the figure of merit, minimum feature sizes as well, tolerances to temperature variations, fabrication errors. That's all part of your figure of merit. And design of a three-dimensional device like this takes about an hour on gaming GPUs. And recently we worked with Google on trying to speed this up, to speed up electromagnetic solver. And on gaming GPUs, we think we can actually speed it up by a factor of 10. So this takes about 1,000 three-dimensional electromagnetic simulations. So even if you are not working on optimization, you know that in commercial electromagnetic solvers, electromagnetic simulations take much longer than 1,000 part of 6 minutes. So we had to actually develop fast electromagnetic solvers and also fast optimization tools in order to handle this and to scale this up. And resulting structure in this particular case, mode converter, exists in traditional photonics. But for greater than 90% efficiency, typically people will do something called adiabatic mode conversion, where you have to slowly expand your waveguide, and that takes hundreds of microns of the chip space. And for us, we can do that in greater than 90% efficiency. We stopped at 90%. It could be as well much closer to 100%, but we're actually happy to stop at 90%. And we can do that in a footprint that is about 2 microns by 1 micron. This is just a layout that you have to etch in silicon. So that's an example. And we've been working on a lot of structures. These are some of the initial designs that we demonstrated. This is a 2-channel wavelength splitter, 3-channel wavelength splitters. For those of you familiar with photonics and optical communications, wavelength division, multiplexing, demultiplexing devices, but very different from traditional approaches that typically involve filters, ring resonators coupled to waveguides. And here are measured results for those devices. They're pretty small. You can pack at least 10 of these into a footprint of a single channel filter. And what is very exciting for us as researchers is that we don't really need any tuning elements. So we fabricate them. Our fabrication is not perfect, but then we go to the lab, we measure all of them and just plot transmission data on the same plot without tuning anything. And transmission for all of the devices that we made line up on top of each other without any post-tuning, which had previously been impossible for the work that we do, and even if you rely on much better fabrication facility. So you'll see in my talk a lot of these transmission results that look like thick curves. These are not error bars. These are basically just overlaid transmission results for multiple devices on the chip. And working on this for a long time, we developed a software suite that we call SPINS, Stanford Photonics Inverse Design Software, that several major companies are now using. We also have open source SPINS B version on GitHub that you can also download and use, and people can also license this SPINS version. But it's kind of quite exciting to see that a lot of people are actually using this, and some groups are developing their own approaches and using it to improve their own photonics designs. So that's kind of introduction to what we're doing with inverse design. And when I gave a talk a few years back, I think this was probably where we stood at that time as well. So we spent last few years trying to show that we can also work with commercial foundries, because when we first started gathering results, of course, all of the devices that we made were done by electron beam lithography. And then we would go to conferences and show our results, and then people would often look at these patterns and say, well, this could never be made in a silicon foundry, right? So this is not scalable. Why are you making robust devices when you can just use electron beam lithography? So we worked with major foundries, AIM Photonics, Global Foundries, IME for the past few years to show that actually we can work with foundries, and now we know that we can. And I'll show you results that we obtained in AIM Photonics as an example. And the process is shown here. We still use our inverse design. We incorporate minimum feature sizes for the process. We just send GDS files, like layouts, directly to foundries. They run their design rule check. They fabricate structures, send us chips back, and we measure them. And here are some of the results. And this was done in collaboration with John Bowers from UC Santa Barbara, who is working very closely with AIM Photonics. So here is the chip, part of the chip that we got access to. We put a variety of devices. Some of those we measured previously. Some of them we hadn't measured previously, but we just wanted to see how they work. And I'll just show you how a couple of them work. So here is one example. This is the 3-channel wavelength splitter that we had previously fabricated at Stanford using electron beam lithography, dry, wet etching. And we measured. I showed you transmission characteristics. It worked quite well, but it was made by electron beam lithography, which is not scalable process. We sent the same design. Actually, we didn't even adjust minimum feature sizes of these devices. We just sent the same designs with 80 nanometer minimum feature sizes, which is what we can reliably make at Stanford. But Foundry, AIM Photonics has minimum features of 90 to 100 nanometers. So there will be a little bit of discrepancy, but tiny bit. But you can adjust, of course, that by rerunning designs. So here is optical microscope image of what we received back from the Foundry. This is design behavior of this 3-channel wavelength splitter, and this is measured behavior for many devices from the Foundry chip. So it's quite a good match. There is a tiny bit of discrepancy coming from the fact that we designed for 80 nanometers and not 90 to 100. And it's pretty comparable to what we saw in e-beam lithography. Here is another device. This is spatial mode splitter converter. So this is a useful thing if you were interested in doing something like multimode photonics, multimode division, multiplexing, demultiplexing for optical interconnects or communications to capture multiple modes on the chip instead of just working in a single mode. So here you have first order mode, just one lobe that's routed to this port. Second order mode, converted to first order mode and routed to this port. And this is 2.8 by 2.8 micron footprint. Again, very, very small block. So I'm showing you here just crosscuts of the structures. So we design a single layer that we pattern. But of course, if you can fabricate three-dimensional structures, arbitrary patterns in 3 dimensions, then of course you can design it. I can't. Axel Scherer probably can, but we still can't. A lot of this is motivated by me trying to do simpler fabrication, as my PhD advisor would know. So here we actually send this to a foundry. We make a cascade of these 2 elements, and theoretically predicted behavior is 2 dB loss in a wide bandwidth of about 200 nanometers. And then we measure performance of the fabricated chip, and it's also around 2 dB in this wide bandwidth. And 2 dB is for cascade of 2 devices. So one device is about 1 dB. So that's quite exciting. Again, there is a little bit of discrepancy relative to theory, but not much. And that discrepancy comes from difference in minimum feature sizes. So it's Foundry-compatible. It is kind of a simple process. You can run it on gaming GPUs. You just obtain layout, you send to a foundry. You can actually build scalable circuits and measure them. So that was kind of part of the motivation that you can make design process for photonics accessible to even people who are not experts in photonics, who don't really know the library of devices that you learn in grad school. Maybe even circuits designers can design photonics. But the other part of motivation was to design things that do not exist already. Can we address functionalities that are not out there, not just make devices more robust or miniaturized, but also make new things that do not exist. And here is one example of the work that was led by my postdoc, Qiyu Liang, who is actually a Caltech graduate. He joined us a little bit over a year ago from the group of Kerry Vahala. So here we show that we can translate the idea that people had already demonstrated in RF photonics, a proposal by Andrea Alou from City University of New York for non-reciprocal transmission in passive structures, where you can achieve non-reciprocal transmission through the circuit by employing intrinsic nonlinearity of the system. So the idea is pretty simple. You have a cascade of 2 resonators, a Lorentzian resonator and Fano resonator. You control phase delay between them, and you can design the system in such a way that coupling to Fano resonator, and this is a Fano transmission, is different in the forward and backward direction. And if the system has nonlinearity, coupling of different power in forward and backward direction would shift the resonance by different amount. And as a result of that, at a laser frequency, which is constant, you will have different transmission forward or backward. So that's a very basic idea that they demonstrated in RF circuits, but to demonstrate it in photonic system without large loss, you had to design all of the elements to match particular transmission characteristics. And doing that by hand is really, really tough, and probably possible, but we would actually spend a lot of time. But doing it by optimization techniques is pretty simple. So we just started from 2 resonators coupled to a waveguide. And then we let our optimization software control the coupling region between these resonators in waveguides to achieve here Lorentzian transmission on the right, and here to achieve Fano transmission that we desire. And here you see optimization process. This is a pretty small structure. Something like this would take less than an hour for sure, because it's pretty small region you're optimizing. And then when you finish and measure transmission, it matches your design behavior, and here as well. And then you can go on and measure this non-reciprocal transmission in two directions. Right? So it's the whole system that behaves in a certain way, not just a single element, but we're designing elements by inverse design. So then we measure transmission. In continuous wave regime, of course, forward and backward, we observe this range, the power range where it exhibits non-reciprocal transmission. But we think that practically this would have the most interesting applications if you're working with pulses. Why? Well, if you're working with continuous wave signals, if you send the signal both forward and backward, you will saturate the system and it would not really work as isolator. But if you are actually working with pulses, in most cases, they would not really arrive at the system at the same time, so you can perform applications, block the pulses from going back into your laser. So here is the result, experimental result showing that that is exactly happening. It's the same system, but measured in the pulse regime. If you are in the right behavior range, you see that reflected pulses in the yellow slots are blocked. They're not really coming back to your source. And your forward pulses are going through. And then if you are outside of that dynamic power range where isolation works, then your backward propagating pulses are not blocked, right? So you're not really blocking anything. And we can actually operate also at the 10 gigahertz range, as shown here, where you see that you're blocking backward signal, even if you're driving signal system at the 10 gigahertz rate. So why is this interesting? Well, it's interesting because it's a pretty complicated function that you can just implement with a tiny block of silicon. This doesn't require anything other than writing these two rings and a little bit of the waveguide in between and optimizing how coupling looks like for the system. So in a case where people would, for example, like to do ranging measurements, and a lot of people are thinking about doing LiDAR, implementing LiDAR using pulses, they have to send pulses and measure the distance relative to the objects from which the pulses are reflected. This is called a ranging measurement, right? And you send some pulses, you reflect them back, and then you have to route them to your photodetector. And you can certainly do that with off-the-shelf components, but you need some high-speed switching, which are pretty expensive and bulky. But here we showed that just by doing 2 extra rings on a silicon chip, we can do the same with high speed in a small footprint with very small insertion loss. It's 0.17 dB insertion loss. And we can actually perform ranging measurements for, we did it for up to 60 meters, right? So you can really essentially pick up your pulses, and instead of sending them back to your laser, you are redirecting them to another output port and sending them to a detector. So that's kind of a new functionality enabled by optimization and inverse design. And maybe as kind of ultimate new functionality, we've also been working on-chip integrated laser-driven particle accelerator, which is a miniaturized version of particle accelerator, right? And I should be careful when I gave this talk first time at Berkeley, I didn't say particle accelerator, and they thought that I was talking about chip accelerator. This is actual particle accelerator, so we're accelerating electrons. So it's really like linear accelerator, but on a chip. So what are we doing here is replacing microwave or radio frequency fields with optical fields, and building stages of accelerator that would perform accelerations on the particles. But you can't really directly shrink the traditional accelerator because metals would actually not really work as well, and components would not work as well if you just directly miniaturize them. You essentially have to structure the electric, and in this case, we're structuring a piece of silicon in order to design the right electric field profile that would accelerate electrons. So here is how a stage of accelerator would look like. I'll show you results in a moment. We've demonstrated a single stage, which is 30 micrometers long. We would couple electrons from here. There is a vacuum waveguide. There is this totally non-intuitive pattern, which would produce right electric field pattern at the location of electrons, so that that electric field always accelerates electrons, incoming electrons. And electrons are incoming with, from converted scanning electron microscope. They have energy of around 80 kiloelectron volts. So in a single stage, we can accelerate them with this gradient, 30 mega electron volts per meter. And we can, in principle, miniaturize accelerator by about 10,000 times. So as you see from the results that I'll show you in a moment, if we cascade about 1,000 of these elements, we should be able to go from 80 kiloelectron volts to about mega electron volt. And mega electron volt is already very interesting because we can actually think about some medical applications or imaging applications. It's not state-of-the-art high energy physics, but it's already interesting for a variety of applications where accelerators are used. And it would be only 1 inch of silicon. So here are results. This is just optical microscope image of accelerator. Everything is integrated. We couple laser pulses through the grating. They propagate down this waveguide, go to the vacuum part where you saw that interesting field pattern. Electrons would really go in this direction, and electric field would be in the direction of propagation. And when we don't have laser on, electrons just exit that stage of accelerator without any acceleration. It's still 83 kiloelectron volts, but when we turn laser on, they're accelerated by about kiloelectron volt. But that's only 30 microns of a space. So you really have gradient of 30 mega electron volts per meter. And if you put another stage after this one and another stage, which from fabrication perspective is not hard, it's basically just the same process. You just write all 1,000 of them. You should be able to get to mega electron volts. And that's what we're working on right now. But we don't really want to cascade exactly the same stages because we think we can do much better than this and achieve larger gradients so that fewer stages are necessary to get to mega electron volt range. So that's another functionality where you can build chip integrated accelerators. And kind of to shift gears, at the beginning I said half of my group works on quantum optics applications, and I'd like to spend the rest of my talk talking about that part. But as you see in a moment, it's not completely disconnected from the things that I've been talking about so far, because we're interested in quantum optics, and in quantum optics, it's even more critical that you don't have losses and that you do things efficiently and you don't lose. Every photon matters, right? So if you are building structures where you want to have greater than 90% efficiencies, you often cannot really use traditional solutions. So just before I talk about that, a brief introduction into kind of quantum technologies. There is a lot of discussion about quantum technologies, of course, a lot of industrial interest, a lot of research labs here and everywhere are working on this. But the bottom line is that for pretty much all of the applications of quantum technologies, and that includes quantum repeaters and networks, quantum computers, quantum simulators, and even quantum sensors that don't require as large scaling as some of these other ones, you need homogeneous long-lived qubits, quantum bits, with good optical interfaces. And I put optical in parentheses because for some of the leading platforms right now, those are microwave interfaces. But having optical interfaces eventually would be really good because you will always have to eventually connect things optically. So people are thinking about transduction from microwave to optical regime and so on. But having optical interface right away, of course, can only be beneficial. And you also need good optical interconnects. And again, you can generalize this to electromagnetic interconnects because you cannot really lose signals along the way as you're connecting qubits. And this is what I'll be talking about, how we're thinking about achieving both of these with the systems of our interest. And I'll start with qubits, and then I'll talk about these quantum optical interconnects. A lot of groups, including here at Caltech, work on superconducting qubits in microwave cavities. And here I'm showing the work from Yale and from Delft, but of course there is a lot of activity in the groups of Oscar Painter and Mohammed Mirhosseini. My team actually works on artificial atoms in optical cavities. And this is very similar to what, for example, Andre works on with his rare earth ions in optical cavities. But we primarily work on color centers in diamond and in silicon carbide. So if you look at the physics of this superconducting qubit in a microwave cavity and this color center inside of the optical cavity, they're pretty much the same, right? I mean, it's kind of same equations govern all of these different platforms. But there are differences, right? So this one is large. You use traditional microfabrication. And it's easy to make all of the qubits the same, right? It operates at microwave frequencies. Everything is defined more or less by traditional lithography. This is smaller by a factor of greater than 1,000. You have to use more different fabrication techniques. Of course, you have to use nanofabrication. Everything, all the structures, features are much smaller. And also to incorporate your qubits, you can't really use lithography to define them as you're doing with Josephson junctions, for example. Here we have to use ion implantation or some other methods where we selectively incorporate impurities into semiconductor. So that's not easy, so it's hard to actually incorporate them at desired positions and with 100% yield. Those are challenges, and that's why that's in red. But there are advantages. I mean, you work with semiconductors. You can also operate at slightly higher temperatures, not at room temperature for most applications, but you don't have to work in dilution refrigerators for most part. You have excellent optical interfaces to begin with. These qubits are already optically interfaced. And which is part that is often forgotten. If you look at the number of even 2-qubit gate operations that you could do per coherence time of the system, it should in principle exceed those for superconducting systems. So you can build larger depth quantum circuits once you scale systems up. Of course, we're not there yet, but you know, we're hoping to get there, and I'll show you how we're hoping to get there. So over the past 5 years or so, we've been primarily focusing on color centers in diamond and silicon carbide, as I mentioned. And we made a switch to these color centers because it had been really difficult to handle inhomogeneous broadening of indium arsenide, gallium arsenide quantum dots, which are excellent quantum emitters, but they have very, very large inhomogeneous broadening. So if you were to build a system where you have to interface multiple of these emitters, it's pretty much impossible. And we shifted to other types of emitters where we can actually have much, much smaller inhomogeneous broadening and tolerate it and control it by a variety of methods. So here in one slide, I'll show you where we kind of stand in terms of quality of qubits in silicon, in diamond, such as silicon and tin vacancy color centers. Over the past couple of years, we've shown that we have excellent photonic interface for silicon vacancy color center in diamond. And this work was done in collaboration with the group of Marco Lonchar at Harvard, and there was also related work at Harvard where it was also shown that there is an excellent photonic interface for silicon vacancy in diamond cavity, and even larger cooperativity than what we saw at 4 Kelvin temperature. So that's all great. I mean, there is excellent photonic interface. That's one desired parameter for the system. Then we've also shown that we can grow these color centers on a diamond chip in such a way that we have only 30 gigahertz inhomogeneous broadening. And this can be seen in this spectrum. For those of you who are experts, spectrum of a single silicon vacancy color center is in red, and spectrum of ensemble is in black. And there is only 30 gigahertz distribution. And 30 gigahertz is much, much smaller than what we had previously had for quantum dots. And as you'll see in a moment, something that we can control and overcome with a variety of methods. So then we'll also shown that we can compensate for up to 100 gigahertz of spectral broadening by Raman driving. And that's a pretty simple technique which people routinely use in atomic physics. So this is your energy level structure of the system. You just drive it with a laser, and you can detune your laser from the upper state transition. And as you're changing that detuning, you are also changing frequency, wavelength of your Raman scattered photon into the cavity. And that experimental result is here, and we can actually change this detuning for up to 100 gigahertz. And 100 gigahertz is much larger than spectral broadening that we have between silicon vacancies, which means that maybe for smaller scale systems, you can just take separate lasers, drive different color centers with different lasers, detune them by the right amount, and always scatter resonant photons which you can interact at the output. So that's very promising, and this result was very promising for us because this was not something we could actually do with quantum dots, as an example. And recently we started looking into alternatives to silicon vacancy color centers, in particular tin vacancy, which has exactly the same structure as silicon vacancy, energy level structure, and also it looks the same in geometry. It's just an extra silicon or tin atom between two vacancies of carbon atoms in a diamond lattice. It's also inversion symmetric, immune to first order, to electric field perturbations, and so on. So it's kind of more immune to environment than nitrogen vacancy center. And this one is exciting to us because it turns out that you can work at slightly higher temperatures. It has much larger ground state splitting, 850 gigahertz as opposed to 50 gigahertz. So you don't really have to cool it down to millikelvin temperatures to see the best results. To avoid phonon-induced decoherence between ground states. So you can work at temperatures of few Kelvin, and it also has higher efficiency, internal quantum efficiency than silicon vacancy. It's simply brighter. You get more photons out because it's detuned from some multi-phonon non-radiative process. So we characterize that, and we're also working actively on methods where we can incorporate these color centers into the lattice without damaging the lattice. Because I mentioned a few slides back, one of the biggest issues and biggest questions, and this is a great topic for people who are material scientists, are how you can make a regular lattice of these qubits, quantum emitters, with as close yield as 100%, right? I mean, can you actually have them at every desired position? And can you make sure that there's broadening, their fluctuations in their properties, inhomogeneous broadening is minimized after you incorporate them in the lattice? And when you just take a block of diamond and you bombard it with ions, that generally is not the result because you bombard it with very high energy ions, and tin is a heavy ion also, and you damage lattice, and any damage in the lattice would introduce strain, and your energy levels broaden, so your inhomogeneous broadening increases. So we've been working with a group of Nick Milosh, who is a material scientist at Stanford, on trying to minimize the damage, but still incorporate these color centers at the right positions. And recently, we developed something that we call shallow ion implantation and subsequent growth, where you implant your ions at a very small energy, much smaller than traditional one 1 kiloelectron volt instead of 370 kiloelectron volts. And of course, that leads to shallow implantation, which is not good for your devices, but then you grow high purity diamond layer by CVD on top. And you can, of course, do mask implantation and introduce them at the desired positions. As a result of this process, a lot of lines that people, including us, couldn't really explain in early papers that were attributed to some other color centers or their different states were basically eliminated because it turned out that they were just coming from the process that was not optimized for growth. And also line widths of transitions are much narrower. So now, having these developed, we're basically using this shallow implantation process combined with fabrication to make devices. And we think that this is much more advantageous than just bombarding with very energetic ions and hoping that things work out. So we also work on silicon carbide. That's another qubit of our choice. In particular, silicon vacancy in 4H polytype of silicon carbide. This has been done primarily in collaboration with the group of Jörg Grafstrup in Stuttgart, and we collaborate with Sofia Economou, who is a theorist at Virginia Tech. And this is a missing silicon atom in a lattice of silicon carbide. And there are a lot of different polytypes of silicon carbide. We like this one. This one kind of hosts the most interesting color centers, in our opinion, and most of the groups doing quantum optics work on this particular polytype. But it has nice properties. It has nice color centers in the range around 900 nanometers, same as quantum dots that we used before. We can actually see that they're pretty stable. This is over hours, 10 hours for this particular V1 transition. And it's just a single missing silicon atom that is producing this particular color center. And we've also shown that we can do Stark shifting with DC voltage. So DC Stark shifting to compensate for to tune it through the all inhomogeneous broadening range of the system. So we can just put electrodes and tune these color centers individually in the system. But in the early work, we could only make pillars you know, as you see in a moment, silicon carbide, kind of like diamond, comes as a block of material. So we had to figure out how to make photonics. Right? It's silicon, it's much easier. You order silicon on insulator, you make devices, and everything works out. But in these materials, it's not so easy. So in order to connect all the qubits, you have to make photonics. And to make photonics, we have to figure out how to fabricate these materials and also how to design them. So now I'm coming to that last part of quantum optical interconnects. How do you connect all of these qubits so that you are not really losing photons along the way and you're not losing information? So the reality of doing experiments in quantum optics is that often we use structures that are not very efficient. So this is from the early work in my group, where we actually measured that, did good photonic interfaces for diamond, right? But in reality, we just had 1% coupling efficiency for that notch. And you know, others also do experiments that way. And this is actually from Andrei's graduate work, which is a beautiful structure. This coupler here had about 5% in coupling efficiency. Actually, that's quite remarkable, because if you look at the work of gallium arsenide, people still use that design. And I remember when Andrei came to me with that design, I told him that that would never work. It would fall apart. Actually, it worked, and people are still using the same design, but it doesn't really have a very high efficiency. And that's okay if you're just probing a single cavity with a quantum dot. But if you want to connect even two of them, you know, all of these losses add up and efficiencies multiply, so you cannot really work with those geometries. So we started combining our inverse design with these quantum optical platforms, but we also had to figure out how to make photonics. And when you have a block of diamond, you have to figure out how you are going to carve structures that are going to guide light. And in early work, we collaborated with a group of Marco Loncher at Harvard, who is my grad school friend. He's also a Caltech graduate, and he developed this technique for angled etching of diamond, which worked very nice for cavities, but the structures that you make are pretty limited because you end up with triangular cross-section. So we wanted to make kind of more complicated circuits, and we adopted this approach of isotropic and anisotropic etching that was initially developed by Paul Barkley, who is also another Caltech graduate. He's now in Calgary. You basically etch down, protect the structure, then etch sideways. And this method is now used by our group and also a group of my former PhD student, Dirk England at MIT, who also works on diamond. So we adopted the methods, changed it a little bit, and combined with inverse design. And these are actual devices made in diamond, right? And they don't look really like kind of intuitive photonic structures, but they do a lot of interesting things. So here is one example. I told you that this coupler has 1% efficiency. So we kind of couple 1 out of every 100 photons, and then you wait for a while, and then you can integrate your photons and do statistics measurements. And that's fine for one node, but would not be fine for more nodes. We wanted to show that we could do better than that, so we redesigned this coupler, optimized the coupler, and actually it kind of doesn't look very different from your couplers, Andrei, but it does have higher efficiency. It actually has 27% efficiency in the same footprint. Theoretically, it can have up to 50% efficiency for vertically symmetric structures, because you always re-radiate half up and half down. But we were here also limited by minimum feature sizes. So in our diamond fabrication, minimum features are 100 nanometers, and you know, I think they're probably a little bit better now. And we also wanted to do it in something that's about 1 by 1 micron. And if you have this notch coupler, 1% efficiency, you kind of wait 10 seconds, and you kind of start seeing something that's probably a cavity. That's how you would do your experiment. And then you integrate longer, and you know, if you have enough signal, then you can actually do some measurement. And here, after 1 second, so after 10 times shorter integration time, you see much stronger signal from the cavity. So you can, in principle, reduce your experimental time by a factor of few hundred. And you can scale it up. We're kind of scaling it up to structures like this, where you have couplers, beam splitters. Here you have 2 resonators with some color centers. You recombine the output. You could use structures similar to this to entangle two qubits, or more qubits if you go to more than that. And this particular result doesn't have qubits yet, but it shows that you can line everything up, and all of the other passive functions work as expected. And then for silicon carbide, I'm kind of quite excited about this. We've been thinking about silicon carbide for a long time. Yeah, and now I was just talking with Alireza Marandi here briefly before my talk. We talked about silicon carbide 5-6 years ago and nonlinear optics, but we couldn't really make photonics at that time. We knew that it has good second-order nonlinearity, and it's a nice material, and people use it for electronics, but we couldn't really make anything other than pillars in these high-quality polytypes like 4H. So silicon carbide may be actually ideal photonics material because it has strong second-order optical nonlinearity, it's piezoelectric, excellent thermal conductivity, large band gap, silicon-compatible, available on wafer scale, and actually hosts high-quality color centers, quantum emitters that I showed you. So you can use it for quantum technologies. And now just a reminder, first half of my talk was on silicon on insulator. You call company like Soitec, you buy wafer and you can do any photonic circuits you like. Silicon wafers were commercialized in 1960s, but silicon on insulator was commercialized in 2000, right before I graduated, and that actually led to silicon photonics entering golden age. Right? Now that's a mainstream material for photonics. And you need this on insulator in order to guide light in the top layer, right? Then lithium niobate, right? Lithium niobate was commercialized, wafers, bulk lithium niobate wafers were commercialized in the 1990s. Lithium niobate on insulator was commercialized in 2010, and now lithium niobate photonics is also entering golden age. There is a lot of activity, and this is from the group of my friend Marco, a launcher at Harvard, but a lot of groups are actually working on lithium niobate photonics. What about silicon carbide? Silicon carbide wafers were commercialized in the 1990s. You can get even 6-inch wafers from companies like Cree. It's very inexpensive, way cheaper than diamond for sure. But there is no silicon carbide on insulator, right? And if there was silicon carbide on insulator, there are a lot of interesting things you could do. And we spent a few years trying to make silicon carbide on insulator. We tried smart cut, we succeeded. We transferred silicon carbide to insulator. Smart cut is ion bombardment, liftoff, bonding. That's what actually people do for silicon. But that damaged material because you bombard it with ions and it introduces unintentional defects. And we want to have only intentional defects, right? Because we are bombarding afterwards to introduce vacancies. And then Daniil Lukin, who actually was an undergrad here, and he worked with Axel and also with Andre. So he worked with my advisor and my advisee, so it was natural for him to come work with me in the next stage of his career. He actually, with Konstantin Dori and Melissa Goodry, developed this technique of silicon carbide for making silicon carbide on insulator, which is actually leading to pristine films. And it's very simple. We start from silicon carbide, then we oxidize silicon wafer, wafer bond, fusion bond silicon carbide onto oxidized silicon, and then grind crystal polishing of the wafer, and finally reactive ion etching for tinning at the end. So it's a very simple process, but there is no ion bombardment. You don't damage your silicon carbide wafer. And we can produce few millimeters by few millimeters chips, which are pretty uniform, make photonics. We have really high quality photonics, so these are kind of arrays of rings. These are inverse design couplers. Right now we use inverse design, of course, to design all of the interfaces and a lot of photonic structures. We have Q factors approaching millions. Also we work typically at around 900 nanometers for color centers, but 1.5 micron for photonics. We can also do nonlinear optics. I said silicon carbide had second order nonlinearity. So first we did second harmonic generation, and for the first attempt it's kind of pretty good efficiency. It's 360% per watt efficiency, and this is measured relative to the power in waveguides. So you have your input in one waveguide, your second harmonic output in other waveguide. They're also inverse designed. And then very recently we also demonstrated optical parametric oscillation. So this is for experts, Chi-3 optical parametric oscillation. 2 pump photons are converted to signal and idler at the output. And we see OPO at 22 milliwatts of pump power. And of course, we should also observe Chi-2 OPO, but we just were lazy and did work at 1500, where it was much easier to do measurement, but we're actually working now on Chi-2 OPO. So that's quite exciting. I mean, nonlinear optics works as the way it should be, and we are moving on there, but also quantum emitters are really good. And they're not degraded relative to the wafer. So when you embed them in these silicon carbide structures, these silicon vacancies are there. They're enhanced when you couple them to cavities. You see 100-fold enhancement on cavity resonance. As you tune your cavity on the emitter, it just lights up. You also see a reduction in radiative lifetime, what we call Purcell enhancement. And this is all for a single quantum emitter, which is proven from the photon statistics measurements. So where are we going from here? This is our plan. You know, in silicon carbide, it's already an insulator. Quantum optical structures are never going to be perfect. I don't think that we will ever have 100% yield of these high-quality qubits. But we can always make the bottom layer, find where the good qubits are, then deposit oxide, and then deposit something like nitride on top, and use that reconfiguration layer to connect the good qubits underneath. And if you are looking into atomic physics experiments, they also have reconfiguration capability, right? When they trap atoms, you never really have a perfect lattice. So then they use something like optical tweezers to reconfigure the lattice, to fill up the empty spots. And you need to do the same in photonics. And we can certainly do that with something like this, which in diamond would be more challenging because structures are suspended, but they don't have to be suspended in silicon carbide. And the other thing that we're working on, and we collaborate with Ignacio Cirac, who is a theorist at Max Planck in quantum optics, and his postdoc, Daniel Lance, and this was done also by my student Raul Travedi and postdoc Shuo Sun, is the idea of doing solid-state quantum simulators. And this idea has been around for several years, and Jeff Kimball here has been working on these solid-state simulators, as atom-based simulators, I'm sorry, but the same proposal, where the idea is to have kind of equivalent of optical lattice, atom array, but you couple it to some sort of photonic structure underneath, and that dispersion of the photonic structure on the mode pattern in the photonic structure would kind of control the interaction between different atoms in the array. And you can achieve also long-range interaction by starting with the structures that have low group velocity, high density of states. And again, people are trying to do that in atomic physics, most notably Jeff Kimball here. But you have to align these atom arrays to a structure that has kind of nanometer features underneath, and that's pretty challenging. And we think that we may be able to do that in solid state and kind of simulate very different spatial problems than what people are normally pursuing in atomic physics, and scale it to larger sizes. So two ingredients that you have to address here are dispersion engineering. Can you kind of build whatever dispersion, whatever group velocity you would like to have inside of the structure underneath, because that's very important. That controls the problems and Hamiltonian you're simulating. And we actually can do that with our inverse design, because we can literally draw the desired dispersion. And manually, you can never really reach that, even in photonic crystals. But with our techniques, you can optimize it to reach the design target for whatever group index you would like to have and whatever is physically possible, and of course with fabrication constraints. And we can also use that dispersion engineering to engineer microresonator dispersion, and if you're building something like a frequency comb, you can actually achieve the flat spectrum. We insert an element which has desired phase shift as a function of frequency, and that impacts the frequency comb spectrum, so you can actually make better frequency combs in principle. And that's kind of the idea of dispersion engineering. So that's one component, engineer the structure. And the other component is, well, what about your emitters? Because they're not all the same. How are they going to talk to each other? And of course, you can tune each emitter separately, but that's never going to work, right? It's really hard, especially if you go to millions. You can't put electrodes on each of your emitters. So with Ignacio Cirac, we're working on actually doing something different. You start from the system that has some inhomogeneity, and then you optimize your driving in order to make them talk despite those inhomogeneities. And it turns out that that's possible. So I'll just show you kind of some preliminary results which show that in the system where you have different kind of broadened spins, you will see some Anderson localization, right? It doesn't look very uniform. Your field would localize at specific spots, and you will not really have spin-spin interaction between different ends of the array. But when you optimize driving on the system, you can remove a lot of that, remove that localization. And that's simply by optimizing optical driving on the system. And we're working on that experimentally, but as the first step, we're showing that this pulse driving actually on color centers in silicon carbide can really lead to the right type of spectrum. This is called flow K eigenstates. It's still for a single emitter. You're just driving it rapidly with microwave pulses. And when you're not driving it, you just see these two lines. When you're driving it with microwave pulses, you start seeing these side bands. And maybe for those of you who are thinking more on the engineering side, you can view this pulse driving idea as producing these side bands on all of these pins, and then these side bands would start talking to each other in the right way. So here are experimental results on the flow K driving. And also this is the same thing, except that we're tuning the microwave frequency. And this pulse driving leads to these flow K eigenstates that are states of the time periodic Hamiltonian or pulse Hamiltonian. It's also related to the ideas of time crystals that people have demonstrated some time ago. So some of you may know also Alex White. He is also a Caltech undergrad who joined my group this year, and he's doing this particular work in collaboration with Daniil and Melissa and Raul. So with that, let me kind of conclude my talk and just say that I talked about different things, but the common theme here is that optimization techniques in photonics are really crucial for scaling both classical and quantum systems. If you're interested in playing with this, we have open source software on GitHub. This is fully compatible with foundry fabrication. If you work with silicon, hopefully there will be foundries for other materials down the road. And you can also enable new functionalities. So I illustrated that with some examples, these non-reciprocal optical ranging measurements on a silicon chip, laser-driven particle accelerator on a silicon chip. And we also actively work on silicon carbide and diamond for a variety of quantum technologies. So that's where we now stand. And of course, I have to show the people who did the work. Also, I already acknowledged our collaborators, and this is our funding. But this is my team from last year. So you may not see everyone here, but pretty much up to date. And I'd like to thank you all for your attention.
Thank you very much.
And actually, I should probably say these are probably your results, maybe, or not even Rabi splitting. No, maybe this is the next generation ones.
Hopefully.
Yeah. Yeah.
Okay, we have
on the shirts. Yeah. Thank you.
Yes. So I have a question regarding particle accelerator.
Yeah.
So it seems like the average energy actually is not changed.
Yeah.
So you're increasing the spread. So you're increasing the temperature over an electron beam. So in real accelerators, they're actually trying to
Yes, exactly. That was not done because here basically electrons are not really synchronized with laser pulses. So some of them would enter at the wrong time and be decelerated. Some of them would enter at the right time. And there are electrons that are not impacted by this. But of course, in real accelerator, you have to address all of that. So that's why you do see electrons that are not affected by the process, and some that are decelerated, and some that are accelerated. There are people who are actually working on bunches and synchronizing electrons with a laser.
So can you actually design something in photonics that can also increase the average energy of the beam, because it's not changed?
Yes, in principle, you could, right? But we have just wanted to show that you could have acceleration. We didn't really think in that direction. But there are a lot of things that you can do on the electron optics side, right? Because we didn't really do anything about that. We just shoot electrons, and then we have a few hundred femtosecond laser pulses. So not all electrons are really, synchronized also with those pulses. But certainly, yes. I mean, that all could be entered into your figure of merit and redesigned. Yeah, Harry.
So it's, well, first of all, Mazel Tov, beautiful stuff.
Thank you, Harry.
And it seems implicitly like you're describing a format for building a scalable system with multiple quantum emitters of build quantum emitters, find them, and then sculpt
Yes.
the local density of states so as to optimally connect them together.
Yes, that's one approach for kind of smaller
yeah.
scale systems, and then for quantum simulator where we're really interested in connecting thousands or millions of them, that approach will not work. So there'll be some empty spots, there'll be some inhomogeneity, so we actually want to control that by pulse driving of the system. And that would also control disorder in the system. So we're thinking of using this to simulate problems where controlling disorder is interesting.
So is there any prospect with the silicon carbide quantum emitters of controlling position with exquisite precision and dipole orientation and things like that?
Right now we're just doing, we collaborate, that's not really shown here, but with the scientists at SLAC who are doing electron beam irradiation. But that is still limited by whatever mask you have or your electron beam size you have. And for producing silicon vacancies, you have to really work in mega electron volts range. So it's not transmission electron microscope. It's beyond that. You need to kind of use smaller scale accelerator. And the best precision that people have, for example, for diamond would be something on the order of 50 nanometers. That's Sandia work using focused ion beam with silicon source. But that, is focused ion beam method, so there are also issues with damaging lattice. We do see better properties when we use CVD, for example, right? So to answer your question, I think this is an excellent research question for material scientists. I would love to see the answer to that, and what we're doing right now with this shallow implantation is an attempt to address that at least temporarily, because we obtain good properties. Yield is not perfect, but at least they're all good, right? And then we can maybe, just start doing some scalable things right away. And it's controlled in that case by the mask. So that's maybe, again, 50 nanometers.
So if you can design an arbitrary photonic element, could you do computation with light, something like what Nader and Get is proposing if you stack several of your elements?
Yes, absolutely. I mean, there are, Nader and Geta has basically used inverse design method, he implemented his own tools, but exactly the same adjoint optimization approach that we were presenting, and you can certainly stack multiple elements and write equations for the system and solve some differential or integral equations. That is certainly possible. He's done it in microwave range. You can map it to optical frequencies. We've been kind of driven by different applications for now, but that is possible because you just need to design photonic elements for a particular role.
Hi. Thanks for
Good to see you.
Really nice talk. I had a couple of basic questions about the inverse design results.
Yeah, sure.
So is there a sense for what the energy landscape of the cost function looks like in these problems? And also how sensitive are the results to the initial conditions that you start with?
Yeah, that's an excellent question. And we've done some work on that. So it's energy landscape for the cost function. So we've analyzed it for certain problems. We were curious about it. We did it for the problem of wavelength splitter and also mode converter. First, even in such a constrained footprint, for greater than 90% efficiency, we can find more than 6 clusters of solutions with greater than 90% efficiency, right? So these are all local optima, and this is local optimization, right? So you can converge one of those local optima, and of course there are some other lower efficiency solutions around that. Landscape depends heavily on the problem, but we know that in order to converge, we know how to initialize the problem in order to converge a specific solution. So we built some intuition around that. For example, when you're doing optimization, you more or less seem to stay, since there are so many good local optima, you seem to kind of go to the first good local optimum, right? So your average dielectric constant seems to stay the same. So if you would like to have something that has more material at the end, you start by initializing with something that has a higher index, or vice versa. So those things we've learned along the way, but landscape depends on the problem. You can't generalize. We did it extensively for few problems, and I don't think you can learn and have a general message on any other problem you would like to solve. Other than it's so rich and this rule of initializing in a certain way that you can apply. And we're working with Stephen Boyd, who is an optimization expert, on actually looking into deriving some more analytical bounds on the at least sizes of devices for particular efficiency, and so that we are not really kind of guessing how big something needs to be for a particular efficiency. So we're hoping to learn more, but I think right now, we did analysis, we clustered solutions, and then you change the problem and it looks different. So you can't generalize. Although all wavelength splitters more or less look the same, but different devices look different.
I have a good question. So what I understand, the silicon carbide is nonlinear
Yes.
that you deposit. What's the nonlinearity? What's the
Nonlinear coefficient is about 2 to 3 times smaller than lithium niobate, Chi2,
Okay.
yes. And I don't know the exact number, but about 2 to 3 times smaller. But on the plus side, fabrication is easier once you have silicon carbide on insulator, and you can have all the electronics and PN junctions and other things. And they're high quality color centers, yeah.
Any other questions? Well, if not, let's thank the
Thank you.
speaker.